Well, hello, welcome to this channel. Today we'll be trying to solve the Navier-Stokes equations. Now, for those of you who do not know what's the Navier-Stokes equations, basically it's this. Read more about of the Wikipedia article to know more. So, basically, the Navier-Stokes equations is where you try to pre predict the flow of liquids in a certain dimensional space. So let's just turn this into a key point over here. So currently all my videos are unedited and raw, cause that's the way that I like it. If you edit those videos, if you edit videos, it's just like hand cherry picked, perfected videos. Now, these types of videos, raw videos, is what I like the best. Raw and unedited footage, just like the garlic bread from Tom Scott's. So, inspiration, Tom Scott, garlic bread, unedited footage. Okay, I'm getting a little bit off topic right now because, like, it's not cherry picked, you know? I didn't even write the script. I just create this dialogue with you viewers at like right now. Like, no dialogue, no script, no pre-planning. I just started this. Well, I might be turning to cherry picked footage, videos, content in the future. So, mind me if I don't have good English. Like, yeah. So, because I'm not native to the English language. So, what is Navier-Stokes? Oh hell no, Xavier-Stokes, Navier-Stokes. Okay, so basically, yeah, predict the flow of liquids in the most easiest sense. Now, I'll be paraphrasing from Wikipedia. The Navier-Stokes existence and smoothness problem concerns the mathematical properties of solutions. Blah 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 blah. Okay, we'll be going to the point. So, for those of you who already know of what Navier-Stokes is, continue watching. Well, the ones who do not know, please pause the video and look and see what Navier and search up what Navier-Stokes is. I bet you're gonna find the article like Wikipedia, and doesn't need to be Wikipedia, that talks about this concisely. So, what is this? So, how do I attempt to Navier-Stokes problems? So there are two problems. Today we'll be doing this smoothness problem. I'll be making like all bunch of these videos until I solve Navier-Stokes smoothness problem. So we're talking about infinite energy and, well, also talking about the infinite smoothness. Okay, so you might not be able to see what I'm doing right now. I'm gonna take some notes. So let's see. So before I made one of these, so let yes. So I switched to freeform because I found out that Pages wasn't working. It took me 10 grueling minutes to figure out that solution. So this might look very raw and it looks very complicated. Now, to you mathematicians out there looking at my video, look, I'm sorry if I don't use proper notation. I just create my own notation. Don't worry, I'm gonna explain it in a minute. So this little notation is called the wave notation, which I found out you could replace with sine. Well, I got lazy, so let's just pretend that this is something sort of like sine, but you how do I explain it? This is in my other one. So basically, this means the two times the two of a1. So for example, this is a1. Let's say that this was a1. Oh my god, this autocorrect. So we get this into a1. Yeah, this is a1. Okay, so this vector is a1. Now, oh sorry. Now this is a1. So now to know what this symbol is, well, it's like, so for example, let's just put this symbol, let's name this, let's just say this symbol and this equation. Okay, let's just take this equation for now, or wait, this is more exact. So this equation, give me a sec, it's gonna take a little bit of time, don't worry. We got like an hour to do this. I don't care. So give me a sec. Opacity. So this will be our equation. Now this will equal to will equal to 2 times e1. Wait, give me a sec. This is gonna take a fairly little bit of time. a1 to I sin x 2. Oh my god. 2 I sine. Give me a sec. Sine x. I sine x. Oh yeah, it's gonna take me a little bit of time because I'm reciting this from memory to n. Which this little equation, let's just so this equation we're gonna copy and go to reform. It doesn't work. Okay, so this equation now equals to this. So it'll be better if I copy this over there. Okay, so this is the equation. So this is the equation we are looking for. So this in sine terms is this. So I'm gonna explain how this works. So recently I made this sort of like invention of a sine term in x, or like a sine term in I, the notation I. So but basically what this means is that this was the remnants of that screenshot trial. So basically what that means is that imagine if I had like this wave over here. Now this is in a positive dimension right now, so it's in like the sort of positive dimension. Now I would be where this thing tilts around, like how many degrees to I, where 90 degrees equals to full tilt to I, and 0 degrees, that means null tilts to I. So okay, so this is the illustration that I quickly doodled up. So this will be the wave, okay? So for this example, the wave, I'll tell you why these equations play a large role in the future, because, well, liquids kind of act like waves, and using this we could explain how they act like these illustrations that I've drawn up. So this might go into the mathematical realm instead of like this intended realm. So we're gonna use I for now. So I is Well, for anyone who doesn't know square root of 1, let me just write it over here for more clarification. So, square root of 1. There you go. This is going to be square root of 1, and this is going to be 1. Where this is going to play a big role, since we're going to be rotating, trying to, like, in quotes, wait, we're going to be in quotes, rotating this wave by I dimension from 1, where we could write it as this. So it's going to be much more. So I'm gonna separate that part out of the equation, which is I sine x, which is equals to rotation of the wave from I1 to I. This, remember, keep this in mind. Okay, keep this in mind. Do any notes that you have, do any notes like related to this. This is extremely important in this theorem, because you can't search up the internet for this. I created wave theory. Well, like personal wave theory, not like things that you would say other things that is wave theory though. So like this is a theory that I came up myself personally, like around a few weeks ago. So rotation of the wave from 1 to I. Now, very simple sketch. So I'm gonna make some notes over here. Example wave. Let's see, just set this to 10. This is gonna be rotation of the wave from 1 to I. Keep this in mind. Like, if you ever need to look back on this, just skip to this part of the video. So let's go back to this. What does A1 mean? Oh, I just said that it was a vector, where this vector is accounted for the intersection of this very straight line to this wave, to one part of the wave. So Navier-Stokes is all about so it's about calculating, predicting the predicting the possible flow of any kind, whether it's for the, so we're gonna use like velocity for v, maybe we're gonna use f for flow, we're gonna use some other variables such as this for rotation of the wave from 1 to I, and this for the main principle of how this works, which means like the basic backbone of this entire paper. So this is unedited paper, okay? So don't judge me. This you can ignore. These are just some rough sketches of what it actually looks like. So this is actually a little bit of Navier-Stokes. So this is like most basic principle of Navier-Stokes, where we have one object interacting with some kind of fluid over here. So using my theorem, we're going to say that this, keep in mind this equation, where this is the air of your fluid that you're interacting with. This is the interaction area, and this is basically means the this basically means the things. Oh wait, means the total area, the entire plane that you have yourself to, and this for a specific area of selected plane, which means like let me get this, which basically means that let's say this is R. Wait, that's the wrong font. So this to the power of 2, since we're dealing with actually power of 3, since we're dealing with 3-dimensional stuff. So this is real numbers to the power of 3. Let's just say this is all natural numbers, we should have included that. So all numbers which is inside of the set, so which is the subsets of, so let's say that 1 for n1. Let's just create a matrix formula right now. It's gonna take a little bit while. Okay, so 1, or like 1 n of 1. Let's say, let's over here, n of 1 2, which is the subset, of R3. Keep this in mind, which equals to, which is subset of R3. Give me a sec. Oh wait, give me a sec. Subset of R3. Okay, so this is the equation. Let's go back. That's basically what this part means. This triangle where I labeled these vertices. Now this will get important. Now you're gonna reason to me. I is the only thing that's interacting with the air molecules. Well, like you also reason that there's like a very simple answer to this. Well, likely only a few of you would reason this because you're my audience. You're smart. So x1, x2. Let's say they make the entire interaction object. So this is x1, this is x2, which we will say as I2. Wait. I2 x1. I2 x1, and let's say it looks like they don't have a thing like that. If you guys spot any mistakes in this demonstration, please comment down below, or maybe the comments will be inside. So let's say union. Okay, let's say union. The union of I2 x2. Look, I'm not really good at subset theory, okay? So I just started learning it like around a few weeks ago. So I2 x1 is a union of I2 x2, and this which is equal to, which will be where this is a union with to the average audience, you'll say, but the union is kind of like the intersection. Well, you're hardly correct. Now you're actually mostly correct, but we're talking about in different contexts in here. So intersection means like intersecting, but like you could say that they're intersecting, like for example, let's just say two circles, okay? Two circles, let's label circle 1 or S1 because I'm too lazy. S1, also it looks better. S1, let's say circle 1 is in the intersection with S2. Now let's say, now this is where the intersection of, where let's say in 2 intersection of the S S1 to will approach infinity, which means like the intersection area. Let's just say intersection area. So intersection area will approach infinity. So intersection area, I did that wrong. So let's just say this is x will equal to somewhere close to 1. Like let's say it's less. It's always less. It's always less than. Give me a sec. I'm trying to find. Oh damn. Yeah, I think I know. Yeah, this is 1. So it'll always be less than 1. So yeah, I don't think I need to write something about this, or like to the average audience. Okay, fine. All right. So intersection will always have areas that aren't conjoined. Like conjoined, let's put that in quotations. Conjoined to each other. But unions are where two sets or subsets can unite. Oh damn it! Almost deleted that. Can unite. Conclusion. Okay. So, explanation for this. Now let's go back to freeform. So yeah, I think you guys know what this means. But what about this? 1/50th. Okay, let's tackle this. 1/50th. Now, I bet like after I teach you one of this, you'll easily understand what this is. So, yeah, basically something like this. So the 1 equals to the subset, like, so this will equal to, the 1 will equal to the, I'm trying to think. So the 1 will equal to the subset of n1. So basically this equal to the subset of n1, which will also equal to the subset, which 1 to the subset of n1 will entirely be a subset of r to the cube. Now this, you're gonna say this only marks like one space, and this only marks one location. Like I can't cheat like that. You're gonna reason. Now this might look unclear, but this basically means that so since this equation is made to tackle with all dimensions, so there's going to be stuff that's going to be out of the ordinary to you mathematicians and physicists and the rest. So this is going to be the same explanation for this one. It's just like this one will have a smaller, a much more less occupied area, or like density, let's just say density, assign the density of this one. So we mark this, we could put in any variable over here, or maybe any variable over here. So let's just say we put in density over here. Put in density over here. Give me a sec. So, oh my god, this arrow, it's so chunky. So, yeah, there we go. Let's just put in density right between this very weird sign and between this. Now, what about this? What about this? This looks so complicated. Please, my master, tell me. Okay, well, this x2 to the power of 2 divided by 2. There are a lot of 2's over here. But just you wait, I'm gonna explain all of them. So, this part means, I'm gonna get this over. So, this will be, this will be when you get a union of this, or like this little thing, this little guy. Oh wait, not this little guy, which is the union. Since I can't type that in here, let's just pretend that this is the union. Cause before I didn't study set theory, so pretend this is the union. And below this is the entire set that we're working with. Now, right now we're trying to calculate how I will interact with this union of this and this given area that it's supposed to collide with the entire area that is which is inside of the given infinite spatial plane. Oh yeah, we're gonna talk about more of that in the next mathematics video. So yeah, I had a little dispute with my friends because they do not know anything about this. So I'll talk about that later. So this basically means set. This is the given plane. Now x1, x2 basically means this. Now why did I write this over here? Why did I write it as a matrix? Cause these two are we will say that these are dependent. These are dependent vertices. So you might not be getting what I'm saying here, cause I'm new to mathematics. Only done it for like 9 or 10 months, like diving into this complex mathematics. So here I means I is the contact area, the point contact area. This is this is where they're dependent. Divide by 2, so you average out the interactions between these. So then you get like a good calculation of it, or like an estimate. This basically is, well, in simple terms, this is an estimate. While like the top part, x1 is this vertice, I is this one, where this one is the given spatial plane plus this vertice and the square of it divided by 2. Cause why will I square this one, not this one? Good question. Because they're dependent right now. So when I say they're dependent, it means that the change of one also is equivalent to the change of another one, even though they have different properties, and they have different places of given symmetry. So yeah, this is just the estimate. Okay, I'm not gonna go that detailed into here, because I explained it very clearly over here. Well, if you have any questions, you could email me. It's available on the descriptions. So this one is just like the one that we did before. This is the wave of x1, x2, because this is wave theory. We're not going to talk about geometrics. So this is an actual illustration where we could smooth out, because for simplicity's sake, we're gonna smooth out this part. smooth out part will look like this. The square root of I squared, because you're gonna extend this to this part. So because right now we're dealing with one vertex. Now if we want to create this into a line or a path of motion, we're gonna turn it into I squared. Now x1 x2 2 to the power divide by 2 to the power of 2 is basically one dimensional way of saying I made a square, or a diagonal way of saying that I made a square. Now this part, yeah, very interesting, looks very very interesting. This is a matrix kind of equation, square rooted. Well, kind of like a pseudo matrix equation, where I simplify, where I extend the equation from this to this. So if you guys want to know how I extend it, please pay attention to this part. So a1 to I, which basically means like a1 to I in this example of the square, it means the square, like the area but of a1 to I over here. So we're gonna make a little square. Made a triangle. So we make a square, and give me a sec. This is a square. Now this is gonna be a1 to I. a2 to I is this one. Let's color code it differently. Let's say that this is cyan. Color code into this color. This is a2 to I. This, and then we're gonna do x1 to I, which is this. Let's color code it still like the same one, because these are all the similar area, and this is gonna be x2 to I over here. Now I add up these parts, so this and this adds up, this and this adds up, and we get a square. Now we divide that by 2 to get this equation, this very very beautiful equation, for a1 to x2 squared, which is this square. Now we divide that by 2 to eliminate the division of this area. So if I didn't do this step over here, we might have ended up with this. So give me a sec. We might have ended up with this equation, which, it looks ugly. So I did some mathematics and ruined and destroyed the possibility. Well, not destroy, like kind of did the mathematics beforehand. Also with the square root, which this square root basically means that I'm not extending this to any higher up dimension than the dimension I'm calculating. Because if I remove the square root of this, we get something that is similar to if we were solving for a square, we get a cube. Okay, so you might have noticed when we first made this, you might have noticed this equation, primarily maybe this equation, which looks very very hostile to our brains for processing. So I'm gonna explain that in later. Basically, this part is V means the velocity of what this triangle is traveling at. And this time we're not solving for the air density it's traveling at. We're solving for when it hits this fabric. Now welded to 2 points. Now let's say it has a flex. It has flex. Now this part means flex, so the bottom part. This is the entire area we're working with. A basically means let's just say the placeholder of the fabric. Now this basically means your fabric interacting with this triangle. Now I'm kind of simplifying and not going as detailed as before, because well, I've already explained a lot over here, made some notes over here and here. Let me just zoom out. So yeah, I'm pretty sure you guys could understand why I'm simplifying over here. So I'm gonna repeat some principles later, but for now, this, yeah, remember that. So let's go into some fancy ones. So this is a new function that I've created, like something that's kind of similar to limits. Cn, which basically doesn't stand for anything, but it is where you have basically it means the decreasing height or increasing height of your waves, or like the trough and valleys of your waves. So over here I made this equation where 2 times 2 by the n of by n divided by x equals to n, which basically means that for each iteration, this might be, so the before iteration is n. Now we deduct the height of n by this equation, which is where n was before previously, to divide by x, which equals to n to the 1, which equals n 1. And over here n minus nx, which equals to your performed calculation. And this is your common wave, where why I didn't use x but used n, because since n is the height of your wave at the very start. So a1, and this is the calculation of the area of the wave, which is 2 times the integral of 0 to let's just call it like this symbol function over x. Now the equation to operate this is log x a, which basically means that we're going to, so this one, the integral is like mapping out the area where we are highlighting. So for example, we have a construction site. Your perimeters that you have set up is the integral. So let's just say that this is the integral. Your perimeter that you have set it up is the integral. These are the minima and maxima of your site, which this might be the minima and this might be the maxima. Let me draw the perimeters. Minima and maxima. Wait. This is going to be your maximum minima, so like the constraints. Minimum constraint and maximum constraint. This is your area or your construction site over here. Now, you might be asking, why can't we just delete all of these useless perimeters and we get the area? It's so simple. Why this dumb? Okay, let me ask you something. So all the viewers that have asked this question might have asked this question. Imagine if we had a construction site and we just started saying, let's just have an area of, say, 78 meters squared. Okay, the area might have looked like this, or like this. Now, not to scale, obviously not to scale. So, we might have an area like this. Now, where are our borders? Where are our constraints? And where is our how do we set the perimeters? Now, you might have reasoned that this is the perimeters, where like these could be set as perimeters, so we could use something like this function. So we could have used where area, let's just say that there's an area of this, which is a A21. Oh my god, why is it not at the right font? Okay, A1. Let's get started. So A1, we could set it as where A1 min A1 to max A1. Give me a sec. Wait, I'm kind of slow with these electronics. So min A1 to max A1. I could have just written this, but no. The integral decides the absolute perimeter. Because if I had just written that, it means that I could still have these alliterations, but I'm just extending this. I'm just making this perimeter like this. It doesn't change the outcome of without your integral perimeter. It's like if you have, it's like here's an easier example. So it's like if you have string, and I tell you to wrap it around some objects like this. I wrap it around this little box. Now, the integral allows us to know how I should wrap it. So just imagine this was 1,000 little objects. If I wrapped it, if the integral told me to wrap it in a triangle shape, so in this shape, now it will be the desired shape that I wanted to be wrapped around. Now, if you were to let yourself wrap it around without any consideration of, well, if you don't have any consideration of the area of the area or like the shape it's gonna become, you might get something that you wouldn't expect. Basically, same logic of what we did. I'm deleting that example sadly because, well, I don't know. It's kind of, let me see my activity monitor. Ah, okay. Yeah, understandable. I'm gonna go. Okay, over here. So, well, you might be interested in this one. Oh, it looks fancy, right? Now, I'm gonna end this video right over here. I'm gonna try to let you viewers try to make an understanding of this. Try to tell me what this means in the comments below, or maybe email me what this means. Whoever emails me this will get a reward, a surprise reward. Well, in the meantime, goodbye. It's been fun with you, and yeah, bye.